I'm really excited about the panel that we've got going. We've got a number of different people who are really pushing innovation and the edge of the types of modeling and methods that we apply for systems planning. I think this is one of the great examples of why eSig is valuable to me, because it's really an opportunity where we've got research, we've got consultants, we've got industry software developers, we've got industry providing insights on what they're working on, all with slightly different perspectives. The only other thing that I'll say is a lot of what we're talking about here today, at least in part, started from discussions that happened here at eSig, 5-10 years ago. Through things like the systems planning working group, we've had task forces on RA that have pushed the limits of the way that we've used to think about it and push the traditional paradigms and modeling that we have done before. So to the extent, if you're here through Thursday and are willing to come to some of the working groups, we've got some great discussion lined up to try to think about what's the next thing that we should be working on collaboratively so that we can continue to push the industry forward. So with that, yeah, please do come Thursday if you can, or join some of our task forces, and you can help influence the way that this panel happens in 5 years. With that, I'll move over to actually hearing from our speakers. So we're starting with Trieu, Senior Energy Analyst from the National Renewable Energy Lab. Trieu.
Thanks, Josh, and thanks, Debbie and eSig, for the opportunity to present, and thanks everybody for joining here today. Let's see, okay, this is working. So yesterday at the really awesome integrated system planning session, Aaron Burdick showed a chart with about 12 models and a spaghetti of connections to link them all together to make an integrated kind of system planning framework work. For this presentation, I'm going to take one piece of that and one spaghetti, and we've hooked it up into maybe more solid, so it's al dente perhaps, and then we're going to see how that helps planning overall. So I have two questions for folks with my presentation. The first goes to modelers, including my fellow panelists here, which is, for what we're doing, does this make sense? How does it compare to what you're doing? General stuff that Josh talked about, that we're having a dialogue. The other is for the consumers of these types of models, capacity expansion, resource adequacy models. Does this make sense to you? Does this give you more confidence in our work, our design, or are we just wrapping our black box with an invisibility cloak and it's harder to really peer in? So those are the two things to kind of think about. So we're talking about resource adequacy. I'm talking about resource adequacy within capacity expansion. I think if you're here, I don't need to go through this. Resource adequacy, obviously an important component of reliability. The key point here is it's the component of reliability that makes the biggest impact, that matters the most within a capacity planning model. I've shown a couple examples here. This is one scenario from one of our studies. The chart on the bottom shows kind of the marginal cost component of different grid services. And you can see there the RA component, resource adequacy, in the red is sizable as meeting just supply and demand. So clearly an important driver to the results of many of these models. But achieving resource adequacy is actually extremely easy. You have a large enough reserve margin, you're resource adequate. But that's not really the challenge. The challenge is that cost reliability trade-off. So how do you have an adequate enough system at lowest cost? That's one of the challenges here that's harder to meet. The second part is computationally. You can hear from different folks here, I think, that will have their own approaches on how to overcome some of the computational challenges. For us, we're looking at scenarios and modeling for nation scale, multi-region, interconnection-wide. So some of those computational challenges definitely keep up here, and we have to figure out ways to overcome them. As Josh alluded to, many folks have thought about this. Many folks have looked at the resource mix changing, and all these studies from the eSig task force, from Berkeley Lab, from DOE, EPRI, et cetera. Many folks from this panel are listed here, and many other studies that I haven't shown here are starting to look at this problem. For us, what is the motivation beyond looking at that literature is, how have we done this before, and is it good enough? And how we've done it before is a traditional capacity credit, having a reserve margin, stacking up your firm capacity after you do your accreditation to see if you meet your adequacy requirement. But what's wrong with that? What's the problem with that? The first is when you do your accreditation, or at least when we do it, there are other sophisticated ways to improve upon this. But essentially, the core of it is when you do your accreditation, it's hard to know where that energy will be delivered during those times of system stress. So you don't really know if you're going to compare your generation profile with your load profile in region or out of region, because you don't know in the future, in a future scenario, where that energy will be served. So that's kind of one component there. Secondly, a lot of these methods use peak load, net peak load as a proxy for times of system stress. That may not always be the case. It's a good proxy, it's a reasonable proxy, but it may not always be accurate. The third component relates to the first one, which is a lot of the formulations around capacity credit or planning reserves don't account for geospatial diversity, don't account for resource complementarity, et cetera. This is I'm sure it's hard to see from the back here, but essentially, you look at all the regions, you look at the lowest wind day, and then you look at how wind is performing in the other regions. And what you observe in the diversity of colors here is the region of interest. Your neighbors may not have the lowest wind days either, so you can rely on their resources. And that applies to demand as well. Same thing, peak demand day over a multi-year period here. Darker color means higher peak, and then the neighbors don't necessarily coincide with that. I think many of us are familiar with that. The thing that I'd want to bring up is when you have a planning reserve, when you have your capacity accreditation, it's hard to fit in that non-coincidence and geospatial diversity benefit within that framework. And lastly, when you use a reserve margin, that's not directly a reliability target. It's not an LLE, it's not an expected unserved energy, and therefore you don't really know if you've achieved that adequacy level that you intended to achieve. Of course, you could iterate, you could change your reserve margin, but in principle, from a capacity planning perspective, the models typically don't have those iterations, and therefore you don't really know for sure. So what are we proposing here, given those limitations of a kind of traditional method? It's a kind of a simple process. I'm going to go through many slides that walk this through, but essentially the idea is to identify those highest stress periods. So let's not use those heuristics of peak load or net peak load. Secondly, let's plan for those days. And when I say plan for those days, use the core of your capacity expansion model, which is optimizing across all the resources in region, out of region to meet those stressful periods. And the third one is check to see if you achieve that adequacy or reliability target, and then you could iterate correspondingly. What does that look like in a fancier flow chart here? So this is how we've implemented it in our national scale capacity expansion model. That's REEDS. So what we do with REEDS is we have our normal periods that capture your economics, your normal dispatch, and then you have a resource adequacy component. And that's where we introduce these stress periods, and we start with some seed stress periods as a proxy. We design the system so it's all co-optimized together, normal operations and stress periods. There's no more planning reserve constraint. There's no more hot period. This is your peak load. You got to have enough firm capacity to that. You just have the stress periods in there. You design your system. You feed that system to the probabilistic resource adequacy suite model, PRAS, that does your Monte Carlo simulation, does the draws of the different thermal plant outages over a multi-year period to estimate your reliability measures, LLE, LLP, EUE. It takes that EUE, expected unserved energy, in the way that we've applied it, looks at it to see, did my reliability target get met? If not, if it does get met, you move on and you solve the next period. If it doesn't get met, you pull the days with highest EUE, you feed it back to your capacity expansion model, and you plan again for it, and you iterate over that loop many times. Oops, wrong way there. Lots of customization. I'm not going to speak to it in the interest of time here, but we could talk about that offline. So what does that look like? So this is the first iteration. You start with your reads, you expand it, you get your capacity. You go over to PRAS, you test your reliability target, whether it's met in any particular region. In this particular example, in the northern MISO area, that reliability target was not met. You feed that back in until you find those days with the highest EUE, feed that back into the capacity expansion model, redesign it. As you can see here, typically that is a light tweak to your portfolio. It's not a wholesale change of things. Then you test it again. If it's met, you move on. It's a pretty simple process there. Some of the key elements that we believe why it's advantageous is you don't know what the sources of stress are a priori. You don't know that. You don't know it depending on your resource mix. And a lot of people ask us this when we apply this. It's like, what happened? How do you know that those days are problematic or stressful? And in some ways, it's totally not satisfying because we shrug our shoulders, say, well, I don't know. But that's the kind of the point here, is because there are multiple sources of stress. It could be high demand. It could be changing demand periods over the winter peaks where your solar and your batteries can't resolve the issues. It could be wind droughts. It could be, in this example here, multiple days of low wind performance in the Pacific Northwest causing this stress. It could be thermal plant outages where we do model temperature correlated outages, higher outages for nuclear plants during the summer, higher outages for natural gas during the winter, et cetera, et cetera. It could be a combination of this, and typically it is a combination of factors working together that's causing those grid stress. And as you see in this last panel here, the days of stress move over time. Vertical axis is time. And so we're really finding those days and we're planning around those days. We don't need to have kind of a predetermined peak load days to do that. And importantly, so that's the problem side. What about the solution side? When you put all of this together, the model is used to find all combinations of solutions to meet those stress periods. All different technologies, so you don't need to think, I'm going to assume X% capacity credit for resource Y. It's going to look at the performance of those technologies. It's going to dispatch them like any other dispatch, like how you're modeling dispatch in normal. That's storage dispatch. It's going to track the state of charge, transmission, remote resources. It's all embedded together and optimizing it together. Okay, so that's the method. Now we're going to kind of demonstrate, perhaps convincingly, I hope, why it matters. So we compare what I just described to our traditional method, capacity credit, and just to convince you that we didn't cherry pick a poorly formulated capacity credit, you can see some of the lines there with declining capacity credit for wind and solar, with increasing generation shares, capacity credit for storage that's not 100% and declining as well, given the limited duration. So we have a reasonable representation of capacity credit and planning reserves to compare with. And what we see when we model the same scenarios, everything else is the same except for the RA methodology. The capacity credit is in blue. The new stress periods formulation is in red. You get lower system costs by a couple of dollars per megawatt hour, or another unit, $160 billion in net present value over a 25-year period or so, and you get higher reliability. So this looks at the normalized expected unserved energy. We have a tolerance in our stress period. We don't actually know what the reliability target is in capacity credit formulation because we did not specify it. It doesn't have a way to specify it. For most regions, you see in the blue, it meets our reliability target, but for certain isolated regions, because we are not exposed to how reliable or unreliable it is, you can have a highly resource inadequate situation as you see there, and you wouldn't know it. So it's both lower costs from the stress periods and greater reliability. And how is this achieved? It's by reducing the amount. How is the lower cost achieved? Is by reducing the amount of overbuilds, if you will. Lots of details in this particular scenario. We don't need to go into it. The key thing here is the stack on the right, which is the stress periods, is lower than the stack on the left. So it's a reduction in generation and storage capacity. If you look into the details here, most of the reductions are in thermal generation and storage. But in some technologies, you actually get an increase in their deployment. So the capacity expansion model sees greater value in that than you otherwise would have. And that's part of the siting problem that I listed earlier, the capacity credit. We misestimated the capacity credit for some resources, in this case wind, to meeting our resource adequacy reserves. And that has a high impact on transmission as well. So again, same colors. Stress periods is in red. Blue is the capacity credit method. These are different measures of transmission. The point that I want to convey is the red lines are greater than the blue lines, particularly for inter-regional transmission. The regions are like the 18 regions I showed earlier. So it's really capturing that value of geospatial diversity over larger scales better, it being the stress periods method compared to the capacity credit formulation. And thereby, it's incentivizing, not incentivizing, it's valuing transmission to a greater degree than the capacity credit formulation by, in this particular scenario, a very significant degree from a transmission build-out perspective. Of course, all this requires interregional coordination in both planning and operations to really utilize that transmission. We recognize that. We recognize that there are barriers to that as well. So in some ways, what I've shown is an idealized, perfectly coordinated system. You can test different levels of coordination and different level of impacts, and we've done that in some of our studies, like the National Transmission Planning Study. Okay, so you might be saying, wait, did you just cherry pick a scenario in which this method is better? And we have tested this over a wide variety, and it's actually very difficult to cherry pick because you're, again, getting lower cost and more reliable systems. So it's hard to find a situation in which that wouldn't be the case. In our particular test that I'm showing here, we're finding it in scenarios with lower renewable generation shares, higher renewable generation shares, but you do see that the gap between that blue and red, it gets larger when you have more reliance on weather-dependent resources, when you have larger systems, when you have greater interregional coordination. So those are important considerations to consider. And with that, to conclude, I think there are a few bullet points here that I won't read, but one of the things that we have confidence in this method is because it is so simple conceptually. In the end, you have a reliability target, you're planning to that target, you know that the grid stressful days are the days that are causing your RA problems. We find those days and we plan around those days. It bypasses all the proxies that you need to do to estimate capacity credit. It bypasses what you might have to assume the performance of different generators are at different time periods. You're just modeling the system directly, and it yields some of the benefits that I spoke to earlier. Obviously, lots of areas for improvement. We could expand the weather conditions. We can improve our outage modeling. Transmission modeling is always tough, and I think you'll hear from some of our panelists there. Multiple reliability metrics. So far, we've implemented this using only EUE as our reliability target. You could have conditions over other targets and iterate over your system as well. And with that, I'll end. Thanks.
Thanks, Trieu. I might just take one moment for a clarifying question from you. The NPV plots next to the reliability metrics, the NPV does not include any kind of drop load in that case.
That's right. We actually, there was a discussion in the first day with the value of lost load. So we did apply that in some of our tests, and it still shakes out. But yes, that's right.
Yeah, you'd likely see a larger discrepancy between the two as you're getting more reliable in the other case. Great. Thank you, Trieu. We're now going to move on to Russ Philbrick. Russ Philbrick is the CEO and CTO of Polaris System Optimization.
Test. Great. Well, that was a great introduction to what I want to talk about because it gets past one of the biggest barriers, I think, to getting to better methods. Excuse me, I got my notes. I don't speak very often, so I have to lean heavily on making sure I say the things I want to say. So Trieu was really getting at the point that capacity expansion factors and resource reserve margins really don't get us what we need in terms of long-term capacity expansion. And that getting more of the details into it about what we really care about, the stress methods, is key. What I want to do is extend what he's just shown to show how we can get more of those details in there, particularly things like how do you deal with chronology appropriately to understand storage effects over all different time frames? How do you get the details of nodal modeling and power flow? Because that increasingly is important in terms of being able to understand the contributions that resources can have to the grid. Understanding the economics, because in the end, economics matter. We're not just dealing with resources that, reliability is not the only criteria. We can't just rely on value of lost load as a metric for economics in our planning of the system. So what I want to show is how we can get those details into there better and some illustrations of what's already being done by folks that you may not be aware of. Okay. So I really have just two steps, and I'm probably going to go through this very quickly and leave plenty of time for questions. The first is just to review capacity expansion concepts and challenges, and then get into some details of computational performance methods. I'm an optimization guy. This is what I really care about, and hopefully you can see some benefits to the work you do. How many folks in here are involved in doing capacity expansion planning that actually run studies and so forth? Yeah, so a good number. You can understand the challenges of getting the details into these models. I just need my glasses. Okay, so first overview of capacity expansion. Capacity expansion is used to answer a broad range of questions about future power grids. It's used to identify installation of new resources and retirements of old. It's used to identify optimal technology choices. It's used or should be used to address coupling between generation expansion, transmission expansion, distribution planning, and customer engagement. It should be used to understand energy systems integration, although it seems like we're a long way from that at this point. However, capacity expansion modeling is difficult because there are many choices, and these need to be evaluated over timeframes that are often decades long. Because the problem is so big, we start with simplified models and add details as we reduce the scope of questions. We can think of this as a funnel that starts wide and approximate and works towards narrowing questions with higher fidelity. In the end, the goal is to balance competing goals of reliability and cost. Too little capacity and we get shortages. Too much capacity and we get high costs. Consider the cost of capacity shown by the dashed red line. Do I have so we can think about cost increasing with the reserve margin. We can also understand that the cost of shortages with increasing reserves will decrease. And if we have not enough reserves, we're going to have high shortage costs. Our goal is to find the right balance identified by the optimal reserve margin. This is then met by stacking contributions from different resources based upon their ability to contribute to the system needs during times of shortage. So this is the ideal of what we should be doing, but this is not actually what we do. Instead, we rely on heuristic metrics such as the 1-day and 10-year standard to determine how much reserves do we get. It's not economics based. These heuristic approaches boil down data that's reflected in costs and benefits that could be used to understand flexibility needs of the system and capabilities of resources. In particular, system variability and resource flexibility interact, and we cannot know capacity contributions or effective load carrying capability until after we have solved the capacity expansion problem, effective what Trieu was saying. So moving on to how we can deal with better improved performance and get better fidelity in these models. The problem with many of our current capacity expansion processes is that we have an incorrect view of what is and is not possible. Current efforts continue to rely on simplified models of the power system, driven by the assumption that we cannot solve long-term capacity expansion with detailed models. Nevertheless, we can. But instead of simplifying system models, this requires that we simplify the chronology to efficiently simulate system variability. Again, Trieu was demonstrating this by using what he referred to as the stress period method. Because of out-of-date assumptions, we continue to use processes. Oops, excuse me a second. Because of out-of-date assumptions, we continue to use processes that are inaccurate and hard. My main message is that we can do much better. We need to do much better. Rapidly changing grid conditions mean that we need to be aggressive on our efforts to adapt planning. Otherwise, we risk creating power systems that are both unreliable and unaffordable. The long model horizon of capacity expansion presents the main challenge. Not only are there many hours in each year, we also need to capture variability of weather seen across different years. Fortunately, the impact of variability can be adequately captured without this level of detail. many hours of a year and across multiple years are similar. Instead, our goal should be to represent variability with a minimum number of scenarios, adding scenarios only when needed to identify the mix of resources needed to manage variability. Again, stress period method. Currently, the most common approach in the formulation is using representative days or representative weeks. Representative day and week allow us to capture variability over the course of a year and over a range of different years, but without needing to include all hours and all years. However, even with the simplification, the number of hours can still be large enough that detailed system modeling is difficult, particularly when including power flow. Solving power flow for a large number of hours can explode computational effort and memory. However, we do have additional choices, allowing us to further reduce the number of system states included in a model. As an example of this, EPRI recently demonstrated the benefits of an alternative representation of chronology to enable storage state of charge management by market operators. Efficient and broad participation of storage in power markets cannot be achieved without some form of state of charge management. However, there is broad concern that if markets attempt to optimize state of charge, participation by more than a modest number of storage resources could become computationally impractical. Nevertheless, by modeling state of charge using a simplified model of chronology, we can replace traditional daisy chain state of charge constraints with constraints that are much easier for optimization, and we refer to this as the wrapper formulation. EPRI applied wrapper constraints to day-ahead storage operations, but this formulation has an even bigger impact on capacity expansion. Our customers have been using this formulation now for over half a decade, and their work has shown that capacity expansion can be solved in much greater detail. In particular, nodal power flow models are practical. This avoids significant challenges imposed by using zonal models, justification for the use of which is rooted in history, where utilities often had sufficient transmission capacity within their own footprint, and impacts of transmission constraints were limited to interconnections with neighbors. However, in today's integrated network, transmission constraints exist throughout the system, and zonal representations struggle to adequately model changing patterns of congestion. Nevertheless, we persist in applying zonal models, resulting in many of the challenges at the front end of integrated planning. We need to define zones that represent changing patterns of congestion. We need to define limits on interchanges between those zones. We need to translate zonal results to provide nodal inputs to other models. And finally, we need both data and people to feed and drive this process. By using nodal capacity expansion models, all these challenges can be significantly reduced. In the next few slides, I'll present a couple of publicly available examples showing that nodal models are practical and are already in regular use. The first example is of work continuing to be done by National Grid, but this was first presented at FERC 4 years ago. In this example, it shows that nodal capacity expansion is practical, but also it shows that nodal capacity expansion has important additional benefits in integrated generation and transmission planning. National Grid continues to use this in their ongoing long-term planning processes to address policy requirements in the Northeast for electrification and decarbonization. To demonstrate the value of integrated planning, National Grid evaluated the generation expansion that resulted from 3 different transmission scenarios. The copper sheet with no transmission constraints, shown on the left. Existing transmission system with no expansion, shown here in the middle. And co-optimized transmission and generation expansion, shown on the right, where new transmission can be installed. Note that the third scenario integrates not just generation and transmission expansion, but also allows optimal selection of transmission projects from among a range of potential projects, recognizing that any one project is likely to require additional investments due to impacts on other facilities. These 3 plots show the results of the 3 scenarios. The first shows the future mix of generation and storage resources required to meet policy goals if we ignore power flow constraints. The second shows changing mix of resources and additional capacity needed if we enforce existing transmission constraints. Significant additional investments required that we miss. The third shows the changing mix of if new transmission can also be built. So instead of having to build all this new capacity, we only need this additional capacity to handle the transmission constraints of the system because we've allowed the transmission system to adapt to the new resources that are being built. So let's focus on some of the differences between these scenarios. Comparing generation identified by the copper plate and existing transmission scenarios, we see a significant increase in generation capacity and also a change in the mix of resources. Though a zonal model might capture some of these impacts, it is nearly impossible to adapt zones to changing congestion patterns over each year and in future years. Also, the efforts to define interchange between zones significantly underutilizes the transmission system or risks producing infeasible outcomes. Comparing nodal scenarios with and without transmission, we see that new transmission significantly decreases the need for new generation. This demonstrates the significant value that integrated generation and transmission planning can have on system costs. This also opens opportunities to improve efficiency of transmission planning. Current transmission planning processes primarily revolve around assessing the reliability of transmission projects, often without a thorough vetting of alternatives. A second, more recent example is work by TCR that highlights the benefits of transmission expansion to enable New England to access Hydro-Quebec storage. In this study, TCR combined a nodal capacity expansion model with a long-term storage allocation model and a detailed energy and ancillary services model. This example and other detailed real-world studies begin to show us that capacity expansion models need not depend on heuristic constraints using capacity reserve margins and resource capacity factors. Instead, capacity expansion can select resources based on their ability to efficiently meet system needs across a range of scenarios, including extreme events. Also, because results are not driven by capacity reserve margins and capacity factors, we avoid all iterative efforts to estimate, apply, and test whether we have used the correct values. Though I have shown that detailed capacity expansion and nodal models are practical and in regular use, there is still more work to be done. There are a range of issues that need to be addressed. How do we understand the value of load flexibility? How do we change planning processes to capture the impacts of operations? How do we bridge the gap between economic and reliability studies? How do we understand the interaction of power systems with other energy systems? There are no technical barriers to addressing these issues, but there is a lack of process to move them forward. In summary, then, I hope I've demonstrated to you that existing planning models are unnecessarily simplified, and that these simplifications result in models that are both less accurate and contribute to making integrated planning hard. However, with appropriate simplifications of chronology, many other system details can be included, allowing us to understand the impacts of variability and the value of flexibility from all sources. As a final note, we also need to recognize that even if technical barriers are not hard, it still is hard to change processes and to help people adapt. And this is where our main challenges lie. Thank you.
Great. Thank you, Russ. Next, we have Kevin Carden, president of Astrape.
Thanks, Josh. Coming through the mic. Great. Appreciate that. Josh introduced me still as the president of Astrape. I'm still getting used to my new title. I was the founder and president of Astrape Consulting for the last 20 years. I founded Astrape in 2005. I'm now the chief product officer for PowerGem. We were purchased by PowerGem, merged with PowerGem in the spring of last year. So it's a little bit bittersweet for me because Astrape was my baby for 20 years, but I'm excited about some of the things that we're going to be doing with PowerGem moving forward, and kind of my role as trying to lean into the synergies that we have between zonal and nodal tools. I want to start off just by echoing or confirming a lot of the things that Trieu and Russ have found, that certainly we agree capacity expansion should not be done with planning reserve margins as an input, ELCCs as an input, that capacity expansion should do endogenous calculation of reliability. We've worked forward and others around the room on this over the years, and that's kind of a key attribute of our capacity expansion modeling in SERVM. But today my discussion is going to be focused on kind of the distinction and the need for both nodal and zonal models and resource adequacy. So I may disagree a bit with some of Russ's perspectives. I think that there are a lot of scenarios required for resource adequacy. A typical study that we will do typically entails 50,000 8760s. So when we're running a scenario, high impact, low probability reliability events, we've got to run tons of combinations of weather years, of load forecast years, generator performance uncertainty. So to understand reliability, we have to run lots of scenarios. So in that particular example, that's just for the base case to determine the PRM. For a typical ELCC study that we run with Aaron Burdick at E3 or with ERCOT, you may do 100 combinations, so lots of portfolios of those. So 100 times 50,000 8760s. For a study we did last year, we ran about 1.5 million core hours over the course of a month to run these scenarios. If we were doing those nodal framework, it takes about 100 times long to run the scenarios. So you're looking at 150 million core hours. That's the equivalent of taking every core at L and running for an entire month. So we're using an entire data center to simulate the effects of data centers on the electric grid. So with that stipulation, our approach is to merge the benefits of zonal modeling and nodal modeling. Do a better job in both zonal modeling, do a better job in nodal modeling to accurately represent the system, fully capture all these events, and not just pull out particular stress periods, but fully test kind of the full distribution of possible outcomes. All right, so my discussion today, kind of what I want to talk through is some feedback loops between nodal tools and zonal tools. So PowerGem owns the Terra software model, Probe, Dazer, so several different nodal tools that are used for transmission adequacy, for production cost modeling, and so forth. How do we use those tools to better construct our setup in zonal reliability modeling in SERVM? And a lot of these tools have been in place and have been in use for decades. Terra has been used as an input to SERVM, so run transfer analysis to understand between these specific zones we've identified, what is the capability of the system. You're typically looking at a summer peak case or a winter peak case to do that. But Terra also has the capability of using a clustering functionality to group buses and generators by electrical proximity rather than by geographical or ownership structures. So better ways of representing the system in a zonal basis, capturing some of the nodal constraints in the system. And I'll talk through that in some detail. The second step is really, what are the feedback loops between zonal models and back to nodal models? One of the limitations that we've seen with nodal models is the deterministic framework of nodal models. Certainly we don't expect that our approach to supersede a lot of the planning that's done in the zonal context, but we do see some supplemental benefit of quantifying the expected value of particular reliability outcomes in these nodal models. So how can we filter down particular scenarios? We shouldn't have to run 50,000 8760s in nodal models to understand the reliability implications, but can we filter down to high load conditions, high net load conditions, low renewable output conditions, high import scenarios, low import scenarios? Lots of ways of filtering those in order to sample appropriate conditions to understand what's the expected value, the expected incremental impact of nodal constraints on the system. We think ultimately that gives us these composite reliability metrics that better inform what the aggregate or composite reliability of the system is. Little intro to SERVM. So SERVM, zonal model, been in use for over 40 years. Southern Company originally developed it. We purchased the software from them, and now it's part of the PowerGem suite of software tools. It is an hourly chronological with intra-hour timescales. So we run renewable integration studies, but the primary use of the tool has been in resource adequacy studies. SERVM is a zonal model, so import-export constraints between zones obviously is a fast zonal model. We don't use a commercial solver for that, so we have embedded logic to perform full economic commitment and dispatch. Our sense is that in order to understand reliability, consistent with Russ's point, we do need to reflect the actual operations of the system. It's not just stacking up resources and comparing to load. It's also taking into account friction that you have between markets. It's understanding the implications of price responsive loads and other economic factors that go in, ancillary service impacts. So in modeling resource adequacy, it's important to replicate the way the system actually works. Our footprint, we cover most of the country. These are just the ISO, RTO, reliability entities. We will be performing interconnection-wide studies with WEC and with all the Eastern interconnection EROs this year to understand kind of wide-scale reliability implications of the current system. Obviously, we have a lot of utilities and ISOs, so some of the blank regions, SRP, see here today, and PNM and APS, other entities in the Southwest are also clients. So we cover most of the country. Most of the country uses SERVM for a lot of their resource adequacy modeling. One particular implementation that we've done a lot of work with recently, and we've got 5 or 6 of these engagements currently ongoing, is understanding kind of interregional value of transmission projects. So doing both nodal assessments on the front end, doing zonal assessments to understand, all right, if I build this big transmission line between SPP and MISO, what is the expected reliability contribution? Derek's done a lot of work in this space as well, but recognizing that diversity between 2 zones could mean that 1,000 megawatts of increased transfer capability could correspond to 2,000 megawatts of ELCC value if there's a lot of diversity between particular zones. So we're doing that work on behalf of a number of entities across the country. Here's an example that we did for Grid United to understand North Plains Connector, the value of that resource. All right, so the feedback loops from Terra into SERVM. So clustering functionality, a project we're working on currently where we are trying to map the Texas system on a zonal basis, but a zonal basis that doesn't respect the regional differences, or sorry, the ownership or geographical differences. It's really about understanding electrical proximity. So in Terra, we run analysis to understand kind of the impact of buses and generators on across flow gates, and grouping those according to similar defects values gives us a better mapping of zones. So we end up with 10, 15 different zones within Texas to better represent those transfer limits for modeling in SERVM. So again, the goal of this, better representations of zones by electrical proximity, better representation of zonal constraints. Using Terra also allows us to not just consider peak summer conditions, peak winter conditions, but other conditions as well to understand the capability. Ultimately, with that better information, we can calculate better zonal ELCCs and planning reserve margins. We've done some work on this in the past with Aiden at EPRI, with ERCOT before. We took particular scenarios, we looked at the transfer limits, and we've seen that there is an impact on the planning reserve margin, for instance. So if you impose transmission constraints based on how we understand the system today, run that in a zonal model. Copper sheet may say an 18% reserve margin gets you to 1 in 10. Representation of these zonal constraints may move it to a 21% reserve margin. So understanding that, and we expect that to be different in different areas across the country. Now, how do we take these results back into Terra to understand or to produce expected value outcomes on the nodal side? So again, kind of similar to the questions that I was trying to ask, how do we sample stress days? We got lots of ideas, lots of capabilities in SERVM to set up filters to say the highest load hours, highest modified load hours, if you've got EVs or data center load or electrification, highest net load hours, sort of by renewable output, the unit category level output, the state of charge of batteries, forced outages, remaining reserves, imports, EUE. So a host of filters available in SERVM to allow you to run those particular snapshots in Terra. the goal of this exercise is ultimately to determine the expected value. So if we take those scenarios, and I've plotted here on the right, the composite reliability metrics out of the two tools as a function of net load. We expect that there will be different heuristics we'll have to use to get convergent reliability results. But the highest net load, we'd expect both from a resource adequacy standpoint and a transmission adequacy standpoint. Those are probably going to be the most difficult time periods to satisfy. The low net load periods, perhaps there are different issues that are surfaced, but if we can define a regression to say from the moderate net load conditions to the most extreme net load conditions, this is the regression of additional expected unserved energy, we can get an expected value, kind of incremental transmission reliability related reliability problems, and then ultimately plan to a particular composite reliability metric standpoint. To skip one slide, in our models, so our expectation is that for the long term, we will have the need for both zonal and nodal models, and our goal is to build the tools within the tools to make the models talk to each other. So we've got buttons in Servum to create Terra input files, have the same thing for Terra to create these zonal import limits in Servum and so forth. So I kind of hit on this one already, but it's taking that regression that I showed on the last slide and layering that in to say, all right, the expected value of composite reliability instead of 1 day in 10, maybe a system that's 1 day in 10 on a zonal model compliant, maybe it's 1 day in 5 on a nodal plus zonal model assessment area. Nobody's defined what the correct reliability standard is yet for that, but ultimately understanding how you translate, all right, what is N-1 secure? How does that translate into expected reliability metrics for the consumer? So again, the goal is solving for 1 day in 10 LOLE or whatever the reliability standard may be. And they have passed new reliability standard that takes into account duration, that takes into account depth of reliability events. So solving for whatever the reliability standard is while also respecting all the nodal constraints. And again, just reemphasizing that we think that it takes a lot of simulations. In the capacity expansion exercise, there are so many asymmetries in weather conditions and generator performance that ultimately running an expected case won't allow you to identify the optimal solution. There's typically some asymmetry that means it's at the 70th percent or 80th percent of the distribution of weather outcomes that drives the need for resources. So ultimately, we see the need for combinations of tools, and that's what we intend to supply to the market. All right.
Thank you, Kevin. Now we'll move on to Derek Stenclik from Telos Energy, founding partner.
All right. Thank you, Josh. Thank you for all the folks on the panel to really tee up this discussion really well. You heard three disparate approaches, but to fundamentally a lot of the same problems. So I think a lot of commonalities around everybody's agreeing on some of the limitations that we have in the process and the tools that we have today. I'm going to agree with all of you on the challenges, a lot of really interesting ways to approach them. And I'm going to kind of add a fourth option maybe to resolving some of those challenges when we think about planning out the system with a lot of uncertainty and a lot of other priorities that aren't just costs. So when we think of capacity expansion modeling, most of that is cost optimization. And we try to come up with the lowest cost portfolio of resources. The reality is there's a lot of other things that go into our decision-making than just cost. And we talked a little bit about the reliability trade-off, but you can think of things like trade-off with emissions and trade-off with land use and trade-off with just preferences around technologies and resource types. So we really wanted to take a step back and look at, well, how do we better manage all of this uncertainty while also tackling some of the fundamental challenges that we see in the capacity expansion modeling? So this is some work we did with GridLab. I'll point you to kind of 3 white papers that came out together. The first really talked about a lot of the fundamentals of the capacity expansion challenges, and that was written by Nick Papas. The second was around this iteration between capacity expansion and directly embedding the resource adequacy constraints, so very much in line with Trieu's approach. And that was written by Elaine Hart. She was supposed to be on the panel, so I'll have a short plug here at the end to cover her stuff. And the third piece of that series was the work that we did around this, what we call just kind of an alternative approach to portfolio design and capacity expansion. So this is my take on where capacity expansion modeling is today. We take a whole slew of inputs and assumptions, we throw it into the proverbial blender of our capacity expansion models, and then we get one output on the back end. And you can just see from the image, my view on that. It's a little bit of a black box. It's pretty messy. It's, as Russ said, it's pretty hard. So what's another way we can do that? And I'll kind of talk through the conventional process first of how we do this portfolio development today in most places, in most regions. And this is really more not on the computational component of it, but just the process. And so today we start out, like before we even do the capacity expansion modeling, there's a whole slew of studies that go into that. Well, what should the fuel price be and the fuel projections be for that modeling? What's the load projection? What are my resource candidates and costs of the resources we want to consider? The PRM and ELCC study, that's an input to the model, and things like retirement plans. So there's a whole ton of work, potentially years or more of work, that go into just developing the inputs and assumptions of this process. Then we're ready to go and do the capacity expansion modeling. Again, that's an intensive, difficult challenge, getting more and more difficult over time. We get the resulting portfolios and we say, okay, now we actually want to test, do these portfolios work? And so if we're, the first step is production cost modeling, and we say, let's evaluate the hour-to-hour unit commitment, dispatch, reserves, and all the other constraints on the system. Maybe do ex post resource adequacy modeling. So, hey, the PRM and ELCC studies gave us the relative reliability or resource adequacy benefits of the different resources, but we know there's a lot of interactions both with the resource mix and the load profile, and so that can change. And so we want to double check that the system coming out of the capacity expansion is actually resource adequate, and then we can look at transmission needs. So it's a pretty long process. You can see a lot of, I think we've focused on the capacity expansion piece, but there's a lot of work that goes just into the inputs, a lot of work that goes on the outputs. The problem we see with that process is there's kind of increasingly stakeholder engagement, that kind of a lot of work being done to improve the inputs and assumptions. And so this process gets to be fairly long. And by the time we get to that final step in the process, all of our inputs and assumptions have changed. And one of the quotes that came out, I forget on which panel yesterday, is like, we do a pretty good job at the inputs and assumptions, but we know all of them are wrong, right? And that's just the reality of it. And then especially when we have an 18, 24-month process, by the time we finish that process, the inputs have changed. And I know a lot of you can relate to this. You've gone through and done a whole study, and then you get to the end and the IRA comes out. And so now we have tax credits that we didn't know about. Or now the capital cost of a combustion turbine is twice the price of what it was 12 months ago. So you can kind of all relate to this. So what's an alternative? Our approach, or the way we're thinking about this, I shouldn't say our approach, we've tested this out, we've piloted it, we're thinking through this and developing some tools to facilitate it. But essentially, is let's take some of the uncertainty around the inputs and assumptions and move it to the back end of that process and have it be very flexible, so we can adjust the inputs and assumptions on the back end rather than using it to seed the capacity expansion. And I think this can be faster, more transparent for stakeholders. It can help bring in multiple objectives, not just cost minimization. It can really help with some of the uncertainty. And lastly, it can be a lot more accessible to the non-modeling community, right? Like this room is collectively kind of experts in the modeling community, but when we're working with stakeholders and regulators and folks that aren't in the models, I think a lot of times the capacity expansion model can be a little bit of a black box where they just get, here's the answer, take it or leave it. And I think this can be a little bit more adaptive. So what is the process? Really quickly, and I'll walk through an example. The first step, kind of select a baseline set of model years. And so one piece of this is we're not trying to do an entire 20, 30-year capacity expansion of every point in time. We're taking a few select years. And I think a lot of you can agree that oftentimes when we do the capacity expansion model, there's a few select years that we're really interested about. When are plant retirements happening? When are emission constraints coming in? And when are there policy targets that we need to plan to? And the idea is this process, you could interpolate between them. But then we identify new resource and specific retirement candidates. So we come up with that list of what are the options that we want to include or exclude from the analysis. Step 3 is where we get kind of deviate from the standard process. So instead of coming up with one optimal solution, we develop hundreds or potentially thousands of unique portfolios. We basically, you could either randomly select those or come up with some heuristics of how you want to sample those. But essentially, come up with a set of many hundreds or thousands of unique portfolios rather than one optimal. And then we'll run each of those through an 8760 hourly production cost simulation across multiple weather years. And so we can get the specific unit commitment dispatch of the system and not do any of the simplification approaches that Russ was saying we can and should move away from. So kind of going to more of a production cost framework. So what does that do? It creates a massive amount of data if we're running hundreds or thousands of portfolios through all of that analysis. And so what we need to do is come up with a way to sift through, filter, and sort the results in a way that we can meaningfully digest all of the information. And so this is what it looks like here. I think this was a case that was run on 1,500 unique portfolios. So there's 1,500 bars there. And here we're ranking them from lowest cost portfolios on the left-hand side, highest cost portfolios on the right-hand side. And then we break down where are the costs coming from. Is it the capital costs, the fuel costs, O&M, emissions? And then lastly, you can see some red there where we're actually embedding the unserved energy cost. So some of these portfolios are inherently unreliable, and we assigned an economic cost to that to either penalize them, or you could potentially exclude any scenario that has unserved energy. But I think it's a unique, that's kind of a feature, not a bug, that some of these portfolios are unreliable, because now we can directly visualize and calculate and quantify the reliability and cost trade-off that we inherently have in our resource adequacy and capacity expansion, but oftentimes that's kind of hidden behind the scenes with our reliability criterion. So now I'll zoom in just on like the far left portion of that chart. We want to look at a set of portfolios that are relatively low cost. Now what you can see is all of these are fairly similar in cost, right? But you can see the makeup of that cost is very different. And you can see the portfolios all the way to the left, the lowest cost portfolios, a lot of fuel cost, less capital cost. But you can imagine if our fuel prices are higher than we expected, you could see how that would reorder and reshuffle these portfolios if we captured that uncertainty. And so the key thing, and then the bottom chart is showing our capacity mix across all of those different portfolios. And you can see similar cost portfolios, but potentially very different resource mixes. I mean, in this case, it's a very solar-centric system. So solar is very similar across them, but you can still see very different portfolios, even with very small deviations in cost. And what comes out of a capacity expansion model is a single least cost option. And sometimes we miss there's similar cost options that might have a very different resource mix. The other thing we can do with this is evaluate kind of multiple dimensions. Again, not just cost minimization, but what you see here is a scatter plot of all 1,500 portfolios. On the x-axis is our renewable penetration as a percentage of load. The y-axis is cost. The shading is our relative wind to solar build out. And then the size of the circle is the amount of storage. And we've made this very dynamic in the tool that we can select any properties on each of those 4 dimensions. So you could very easily flip, hey, I want to look at land use as a function of my portfolios. What might that look like? And you can see where some of these trade-offs might occur. And in case it wasn't clear, the kind of the tool and the process we've done to set this up is the fuel costs, capital costs of the equipment, all of those properties that are typically inputs, we are now post-processing on the back end of the production cost simulations. So we can adjust the fuel costs and immediately see how this chart or the previous charts might change given that change in fuel price or a change in technology cost. So quickly, what are some of the benefits and differences with how kind of conventional capacity expansion modeling is conducted? I walked through most of these, but again, conventional capacity expansion modeling, typically you get one optimal solution. It says, given all my inputs, here's the single cost optimal, here's the ideal portfolio. The alternative to that is we get hundreds or thousands of potential portfolios. We can capture that uncertainty, and we can, importantly, start considering non-cost metrics against each portfolio. So if we have a dozen portfolios that are very similar costs, maybe land use becomes more important, and that determines the portfolio we want to select. Or maybe some stakeholders don't want offshore wind or don't want hydrogen or something like that, and we can filter and exclude portfolios based on technology preferences. Second, conventional capacity expansion modeling. A lot of the folks already talked about the simplified chronology and transmission and grid operations that have to go into that computation. The alternative here, because we're doing the full 8760 chronological modeling, there's less simplification required. We're doing the full 8760 to better account for variable renewables and storage, charge, and discharge constraints. And if we want to, we can directly embed transmission into that analysis as well. So a lot more granularity. Again, a similar critique that we heard a lot about, maybe an alternative approach to resolving it. Third is around resource and fuel costs must be determined before modeling. Again, because we're doing this after the fact, we're able to make adjustments to the fuel and resource costs and then post-process. Right, we're not optimizing based on those decisions. We can post-process what the impact of those costs will be. Now, an astute observer might say like, "Hey, shouldn't fuel costs change your unit commitment and dispatch?" Absolutely. I would say, this isn't taking into account like coal versus gas trade-offs between the two. I would argue that is getting less important in our kind of forward-looking projections. So it is assuming that the unit commitment and dispatch is based on a specific price, and then we're post-processing changes to that. And so that allows us to do sensitivity analysis around key assumptions and uncertainty. We can very quickly, we don't have to rerun the model to say, hey, what would a $20 carbon price do across these different portfolios? We can see that on the back end and very quickly adjust, refilter, resort all of our portfolios. And same with things like policy changes around the ITC and PTC. If policy changes happen, we don't have to go and rerun the model. We can just adjust the CapEx or the price on the back end. Again, resort all of those portfolios. It'll dynamically change the ordering of all of those charts, and we can visualize the results very quickly. Fourth, I think this is probably the most valuable benefit is today, the capacity expansion modeling is typically utility-led modeling. Stakeholders are kind of reviewing the inputs, reviewing the outputs, and providing feedback there. But they're ultimately, in most cases, not running the models themselves. And to them, it's a black box. And so the alternative here is because it creates a dashboard of 1,000 different portfolios, stakeholders can very quickly go in and be like, well, I prefer a portfolio that looks like this. How does that rank up against this portfolio? And it's not reliant on the utility to provide those to the stakeholders. The stakeholders can go in and do their own filtering, their own, bring in their own factors to decision making. Fifth, capacity expansion modeling is very computationally challenging. It takes up a lot of resources to come up with an optimum solution, a lot of memory, a lot of RAM. We typically are constrained on compute capability. And again, that's what's driving a lot of that simplification. This process, still a lot of compute requirement, but it's parallelized computing. It's not optimization. And so we can split the problem into as many parallel 8760 production cost simulations, run that through. It's a lot easier than, again, trying to do that optimization. And then lastly, a lot of work done to talk about the PRM and multi-dimensional ELCC surfaces that are required for conventional capacity expansion modeling. And this is a different approach to resolving a similar challenge of how do we resolve that and directly embed unserved energy and constraints like that into the model. So with that, I'm going to skip over a couple things. I will say there's a demo. So if you go telos.energy/demo, you can play around with the tool. You can develop your own portfolio. You can filter things like, I don't want to look at cases with wind, or I want to change the fuel price or the CO2 price. Very interested. It's, I would say, a pre-beta version of the tool, but something we wanted to give people the ability to tinker around with, and very interested to hear your feedback.